A paperclip sits on a table. A cheap fridge magnet lifts it off the surface. That magnet just beat the gravitational pull of an entire planet. Think about that. The force holding every ocean, every mountain, and every human being onto the Earth lost to a $2 magnet. Gravity is the oldest force we know. It built the solar system. It keeps the moon from flying away. It guided every rocket ever launched. And yet right now, in 2026, physicists will tell you they have no idea what gravity actually is. We know how it behaves. We do not know what it is. Isaac Newton gave us the math in 1687. Albert Einstein gave us something wilder in 1915. He said gravity is space itself bending. And that model works perfectly. Until it doesn't. At the smallest scales in the universe, Einstein's equations collapse completely. The math spits out impossible answers, infinities that mean nothing. Meanwhile, a force nobody named or predicted is tearing the universe apart right now. It outpowers gravity on a cosmic scale. Scientists call it dark energy. They have no idea what it is. That's where we are. The force that built planets is still unexplained. If you enjoy the journey, hit like and subscribe so you don't miss what's coming. One of the deepest mysteries in science. Prepare yourselves. We begin. Newton did not discover gravity. Gravity was always there. What Newton discovered was that gravity follows rules, and that single idea, written down in 1687, changed everything. The story starts with an apple tree in England. Isaac Newton was sitting in his garden when he watched an apple fall. He did not ask why it fell. Everyone knew things fell. He asked something stranger. He asked whether the same pull that dropped the apple could reach all the way up to the moon. That question sounds simple. The answer rewired the universe. Newton worked out the math. He showed that every object with mass pulls every other object with mass toward it. The bigger the object, the stronger the pull. The farther away, the weaker it gets. He wrote it all into one clean equation. And that equation worked. It predicted the orbits of planets. It explained the tides. It let engineers calculate where a cannonball would land before it was ever fired. For more than 200 years, Newton's gravity was the law. Full stop. Engineers used it to build bridges. Astronomers used it to map the solar system. When scientists finally launched rockets into space, they used Newton's equations to plot the path. His math-guided missions to the moon. It is still used today for most calculations inside our solar system. But here is the crack in the foundation that nobody could ignore forever. Newton's equation told you how gravity behaved. It gave you the numbers. But it said absolutely nothing about what gravity actually was. How did the Earth reach across 93 million miles of empty space and pull the sun? How did the moon feel the Earth's tug without anything connecting them? Newton himself admitted he had no answer. He wrote that he would not pretend to explain the mechanism. He just knew the math worked. That honesty was rare, and it masked a problem that would take 2 more centuries to fully surface. Think about it this way. Imagine you can move a cup across a table without touching it. You can predict exactly where it will slide and how fast. But you have no idea how you're doing it. That was Newton's gravity. Perfect numbers. Then, something strange happened in the 1800s. Scientists discovered that light travels at a fixed speed. Nothing moves faster. That discovery seems unrelated to gravity. It wasn't. It was the fuse on a bomb that would blow Newton's model apart. If gravity acts instantly across any distance, as Newton's equation implied, then it travels faster than light. That violates everything physicists were learning about how the universe works. Something had to give. A young man in Switzerland, who worked as a patent clerk, started thinking about this problem around 1905. His name was Albert Einstein, and he was about to do something that had never been done before. He was not going to refine Newton's answer. He was going to throw it out entirely. But before we get to Einstein's revolution, sit with this for a second. Newton built a model so accurate it guided spacecraft across the solar system. He did it without knowing what gravity was. The math was right. The picture underneath the math was a blank. For over 200 years, the most powerful force shaping the universe around us was running on equations with no explanation attached. That blank space is still there today, just much, much deeper, and what Einstein was about to draw inside it would raise stranger questions than Newton ever asked. Albert Einstein was 26 years old when he rewrote the rules of time and space. He was not working at a university. He was reviewing other people's patents at a government office in Bern, Switzerland. And in his spare time, he was quietly dismantling 3 centuries of physics. His first big idea came in 1905. He showed that time is not fixed. It stretches and shrinks depending on how fast you move. That alone was shocking, but it was just the warm-up. The main event came 10 years later, in 1915, when Einstein published the general theory of relativity. And the core idea is so strange that most people hear it, nod, and then miss what it actually means. Here it is. Gravity is not a force pulling things together. Gravity is the shape of space. Let that sit for a moment. Imagine a bedsheet, stretched flat and held tight at the corners. The sheet sags. It curves down around the ball. Now roll a marble across the sheet. The marble does not travel in a straight line. It curves toward the bowling ball, following the slope of the sheet. From above, it looks like the bowling ball is pulling the marble, but nothing is pulling anything. The marble is just following the curved surface. Einstein said the universe works exactly like that, but in 3 dimensions of space, plus time. Mass bends the fabric of space and time around it. Other objects moving through that bent space follow the curve. That curving path looks like attraction. It looks like a pull. But the attraction is geometry. It is the shape of space itself. This was a complete replacement of Newton's picture. Newton said objects pull each other. Einstein said objects warp the space between them, and other objects follow the warp. The wild part is that Einstein's version is more accurate. It predicted things Newton's model never could. It said that the path of light would bend around massive objects, because light follows the curves of space, just like everything else. In 1919, during a solar eclipse, astronomers measured starlight curving around the sun by exactly the amount Einstein predicted. Confirmed. The world paid attention. His equations also predicted black holes, regions where mass is so concentrated that the curve of space becomes a one-way tunnel. Everything falls in, nothing comes out. Even light gets trapped on the slope. Einstein's model also explained why time slows down near heavy objects. The more mass you have nearby, the more space and time bend, and bent time runs slower. This is confirmed. The GPS satellites above your head have to correct for it constantly because they sit farther from Earth's mass than we do, so their clocks tick slightly faster. Without that correction, GPS would drift by several miles per day. So Einstein gave us a picture, a visual, curved space, bent time, objects rolling through warped geometry. And for the large-scale universe, it works perfectly. Black holes, galaxy orbits, the bending of light, the behavior of the cosmos. Einstein's model handles all of it. There is just one place where it completely falls apart. The very small, when you zoom in past atoms, past protons, into the world where quantum physics rules, Einstein's equations stop working. They don't just get less accurate. They break entirely. And the reason they break is something physicists have been arguing about for nearly 100 years. The next chapter goes to the level where the breakdown begins, and what lives there is unlike anything you've pictured before. May 29th, 1919, 2 ships are positioned on opposite sides of the Atlantic Ocean. One is anchored off the coast of West Africa. The other is near a small island in the South Atlantic called Principe. Both teams are waiting for the same event. a total solar eclipse. The man behind both expeditions was Arthur Eddington, a British astronomer. He had read Einstein's general theory of relativity and believed it. That took courage. Most of the scientific world still trusted Newton. Einstein's idea that gravity was curved space was seen as interesting but unproven. Eddington wanted to change that. The plan was elegant and dangerous. During a total solar eclipse, the moon blocks the sun completely for a few minutes. In that window of darkness, stars near the edge of the sun become visible. Einstein's theory predicted that the sun's mass would bend space around it, and light from those stars would curve as it passed close to the sun. The stars would appear to shift slightly from their normal positions. Newton's model also predicted a small shift, but Einstein's number was exactly twice as large. If the stars shifted by Einstein's amount, Newton was wrong. Eddington photographed the stars during the eclipse. Then he compared those positions to photographs of the same stars taken months earlier, when the sun was nowhere near them. The shift matched Einstein. Precisely. The news broke on November 6, 1919, at a joint meeting of the Royal Society and the Royal Astronomical Society in London. The announcement was treated like a scientific earthquake. Headlines ran across newspapers the next morning. The New York Times called it one of the greatest achievements in human thought. Einstein, almost overnight, became the most famous scientist alive. But here is what most people gloss over. The measurement was hard. The photographs were difficult to take. There was cloud cover on Principe that nearly ruined everything. Eddington's team worked through it and got just enough clear images. The margin for error was real, and some scientists at the time argued the data was not conclusive. A few even suspected Eddington was too eager to confirm Einstein. Those doubts did not last. Over the following decades, better measurements confirmed the result again and again. The bending of light around massive objects is now one of the most tested predictions in all of science. Astronomers use it constantly. When you see photographs of galaxies bending light into arcs and rings around them, that is Einstein's prediction, confirmed in real time across billions of miles of space. The effect even has a name: gravitational lensing. Galaxies act like natural telescopes, bending and magnifying light from objects behind them. Scientists use this to study things too far away to see directly. So 1919 settled the debate between Newton and Einstein. Einstein won. But winning that debate opened a much harder one. Because if gravity is the shape of space, then what shapes it at the tiniest level? What happens when you shrink the stage down past atoms? Does space still curve? Does the geometry still hold? Quantum mechanics had answers to what happens at tiny scales, and those answers had nothing to do with curved space. They had nothing to do with geometry at all. Two perfect models, two completely different pictures of reality, and they cannot both be right. Something is waiting in that gap between them, and what physicists found when they tried to close it still has no solution. Pick up a paperclip, hold it between your fingers. Now bring a refrigerator magnet close to it and let go. The paperclip snaps to the magnet instantly. You just watched gravity lose a fight. The entire mass of the Earth, 6 trillion kilograms, was pulling that paperclip down. A $2 magnet with almost no mass at all pulled harder. That is not a demonstration of how strong magnets are. That is a demonstration of how staggeringly weak gravity is. Physicists call this the hierarchy problem, and it is one of the most embarrassing unsolved puzzles in all of science. Here is the scale of the problem. Gravity is roughly 10,000 billion times weaker than the electromagnetic force. That is not a rounding error. That is a gap so enormous that no one has a satisfying explanation for why it exists. Think about what that means in real life. You are standing on the ground right now because gravity is pulling you down. But the only reason you don't fall through the floor is the electromagnetic force between atoms in your feet and atoms in the floor. Every time you take a step, electromagnetism defeats gravity instantly without even trying. Gravity is only noticeable at all because it works at huge scales and has no off switch. It always attracts. It adds up across planets and stars and galaxies, but particle by particle, force by force, it is the weakest thing in the universe. The physicist Richard Feynman once described it this way: a person falling from a 200-foot building is pulled all the way down by gravity. Then the electromagnetic force between atoms in the ground stops that person in a fraction of an inch. The whole journey down versus a fraction of an inch to stop. That is the difference in power. The other three fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, all operate at similar levels of strength. They fit together in a mathematical framework called the Standard Model. Scientists can write equations linking them. The numbers make sense relative to each other. Gravity refuses to fit. Its strength is so far outside the range of the other forces that every attempt to include it in the same framework produces equations that fall apart. One theory tries to explain the gap. Some physicists think gravity might be leaking into other dimensions. In this idea, the universe has more than the 4 dimensions we experience. Gravity spreads out across all of them, thinning out, growing weaker in our dimension, while its full power is diluted across the rest. The other forces stay locked in our dimension and keep their full strength. This is still a theory. There is no confirmed evidence for extra dimensions, but it is one of the few ideas that gives a reason for the gap, rather than just measuring it. What makes the hierarchy problem so frustrating is that it is not a small discrepancy. If gravity were just a little weaker than the other forces, physicists might write it off as a coincidence. But this gap is so extreme that coincidence feels impossible. Something is missing from the picture, and the search for what is missing leads directly into the strangest territory in modern physics. Because the hierarchy problem is not just a question about gravity's weakness, it is a clue that the universe might be built in a way we have not figured out yet. What comes next goes even deeper, into the level where all 4 forces are supposed to meet, and where the meeting keeps going wrong. Everything that has ever happened in the universe came down to 4 forces. Every explosion, every heartbeat, every star that ever burned, every atom that ever bombed. 4 forces built all of it. The first is gravity. You already know it. It pulls mass toward mass. It holds planets in orbit and keeps you on the ground. It works across any distance. It never pushes. It only pulls. This is the force behind light, electricity, and magnetism. It is what makes your phone screen glow, what powers every circuit, what holds molecules together. It is what stops your hand from passing through a wall, because the electrons in your skin repel the electrons in the wall. Electromagnetism is roughly 100 million times stronger than gravity. Those are not typos. The third is the strong nuclear force. This one works only inside the nucleus of an atom. It is the force that holds protons and neutrons together. Without it, every atom would explode instantly. The strong force is the most powerful of the 4, but its reach is extremely short, smaller than a single proton. The fourth is the weak nuclear force. This one drives certain kinds of radioactive decay, the process where unstable atoms break down and change into different elements. It also makes the sun burn. The fusion reactions inside the sun depend on the weak force to convert particles and release energy. It is weaker than the strong force and electromagnetism, but still vastly stronger than gravity. In the 1970s, physicists managed to link 3 of these forces together: electromagnetism, the strong force, and the weak force were unified into one mathematical framework called the Standard Model. It is the most tested theory in science. Its predictions have been confirmed to extraordinary precision in particle accelerators around the world. Gravity is not in the Standard Model. It was left out. Every attempt to add it has failed. The problem is not that gravity is too complicated to describe. Einstein described it beautifully. The problem is that Einstein's description and the Standard Model's description use completely different languages. Einstein's gravity is smooth geometry, continuous curves in space and time. The Standard Model is about discrete particles, tiny chunks of energy exchanging force carriers in sudden jumps. These two languages do not translate into each other. When physicists try to force them together, the equations produce answers like infinity for things that should have real finite values. That is a sign the math is broken, not a sign that infinities actually exist in nature. So right now, the best theory of the very large and the best theory of the very small sit side by side, unable to merge, like two puzzle pieces that look like they should fit, but physically cannot. The three forces inside the Standard Model at least speak the same mathematical language. Gravity shows up speaking something entirely different, from a completely different framework, following different rules. Every other particle in the Standard Model has a partner force carrier. The photon carries the electromagnetic force. The gluon carries the strong force. The bosons carry the weak force. Gravity should have one too. It does not have a confirmed carrier, and that missing piece, that ghost particle at the heart of the world's weakest force, is where we go next. Zoom in. Past skin, past cells, past molecules, past atoms, past protons and neutrons. Keep going. At a certain point, the rules change completely. This is the quantum world, and in this world, gravity has almost nothing to say. Quantum mechanics is the science of the extremely small. It describes how particles behave, how they interact, how they carry energy, and it is, by the numbers, the most accurate theory humans have ever built. Its predictions match experiments to more than 10 decimal places. No other theory in science comes close to that level of precision. But quantum mechanics describes a world that looks nothing like the smooth, curved space Einstein drew. In the quantum world, energy does not flow continuously. It comes in discrete chunks called quanta. Think of it like the difference between a ramp and a staircase. Einstein's gravity is a ramp, smooth, continuous, always sloping. Quantum mechanics is a staircase. You jump from step to step. There is no in-between. Forces in the quantum world are carried by particles. When two electrons repel each other, they do it by exchanging photons. The photons carry the force between them. This exchange happens constantly, billions of times per second, and the math describes it with extraordinary accuracy. Every force in the quantum world works this way. Particles exchange force-carrying particles. The force exists because of those exchanges. Gravity does not fit this picture. At the scale of planets and stars, gravity dominates everything. It is the architect of the large-scale universe. But at the quantum scale, the scale of atoms and particles, gravity's influence is so tiny it is effectively zero. In particle physics experiments, physicists routinely ignore gravity entirely. It is that irrelevant at small scales. This is not just inconvenient, it is a sign of a deep problem. The universe is made of quantum particles. Planets are made of atoms. Atoms are quantum. So the force that holds planets in orbit must at some level operate on quantum particles. The large and the small have to connect somewhere. There has to be a quantum version of gravity. But when physicists try to write the equations for quantum gravity using the same methods that work for the other three forces, the math produces nonsense. Infinities appear everywhere, not helpful infinities that cancel out, infinities that mean the calculation is broken. This is called the non-renormalizability of gravity. It is the technical name for a fundamental failure. The quantum toolkit that works perfectly for electromagnetism, the strong force, and the weak force completely breaks when applied to gravity. So here is where things stand. Einstein's gravity works at large scales. Quantum mechanics works at small scales. The universe contains both scales. At the boundary between them, like the center of a black hole or the first instant of the Big Bang, both theories must apply at once. And both theories fail there. No equation survives. No prediction comes out clean. The math returns answers that mean nothing. Physicists have known about this failure for nearly 100 years. They have not fixed it. Something is missing, a deeper layer of physics that nobody has reached yet. And the search for that missing layer has led scientists into some of the strangest ideas ever seriously proposed. In 1916, Karl Schwarzschild was serving in the German army on the Russian front during World War I. He was also, in his spare time, solving Einstein's equations. He found a solution, a perfect mathematical answer to what happens when you compress mass into an infinitely small point. The equations gave a clean result, a specific radius around that point where space curves so sharply that nothing can escape. Schwarzschild sent his solution to Einstein from the trenches. Einstein was impressed. He called the math elegant, but there was something neither of them fully confronted. At the center of that solution, at the actual point of infinite compression, the math does not give an answer, it gives infinity. And in physics, when your equation returns infinity, it means one of two things. Either something real and infinite exists in nature, which is almost never true, or your equation has reached its limit. It has broken down. That central point is called a singularity, and singularities show up whenever gravity is pushed to its extreme. The center of a black hole, the moment before the Big Bang. Any place where mass becomes infinite and space collapses to a point, Einstein's equations hit the singularity and stop working. Quantum mechanics hits the singularity and also stops working, but for different reasons. And when physicists try to force both theories to work together at the singularity, the equations return answers that are meaningless. Not approximately wrong, mathematically nonsensical. Here is what that looks like in practice. When physicists use quantum field theory, the method that works perfectly for the other three forces, to calculate how gravity behaves at the quantum scale, a specific kind of result keeps appearing. Corrections to the calculation generate new terms. Those new terms generate more corrections. Each correction is larger than the last. The series never converges. The answer keeps growing without limit. This is called ultraviolet divergence. The math runs away to infinity and never comes back. For electromagnetism, a clever trick called renormalization fixes this problem. You absorb the infinities into the measured values of things like electron mass and electric charge. The infinities cancel, the calculations work again. Physicists have used this trick to make extraordinarily precise predictions. Gravity refuses to be renormalized. Every time physicists try the same trick, new infinities appear faster than they can be absorbed. The theory generates an infinite number of parameters, each requiring a separate measurement to pin down. A theory with infinite free parameters explains nothing. It has no predictive power. So the math breaks, completely and unavoidably, every time gravity is pushed to the quantum level. This is not a small technical issue waiting for a clever fix. It is a structural failure. It tells physicists that the framework being used is fundamentally wrong at that scale, that something deeper is missing from the picture. Schwarzschild died of disease on the Russian front just months after sending Einstein his solution. He never saw the full weight of what his math implied. The singularity he uncovered, where the equations die, is the same singularity that defines the boundary of our understanding today. Every black hole in the universe contains one, and one sits at the starting point of the entire universe. Physics stops there, and just beyond that stopping point, something strange awaits. Somewhere in the constellation Sagittarius, about 26,000 light-years from where you are sitting, there is a black hole 4 million times more massive than the Sun. It sits at the center of the Milky Way. Every star in this galaxy, including the Sun, orbits it. You cannot see it directly. No light escapes from inside it. But astronomers have watched stars near the galaxy's center moving at extraordinary speeds, swooping around an invisible point, pulled by something with immense gravity. The black hole's presence is confirmed by what it does to everything around it. Now zoom in. past those orbiting stars, past the bright disk of gas being pulled inward, past the edge where gravity becomes inescapable, a boundary called the event horizon. Inside that boundary, physics changes. Inside a black hole, the direction of time and space swap roles. Outside a black hole, you can choose to move left or right, forward or back. You cannot choose to move backward in time. Time only moves one direction. Inside a black hole, space collapses inward so completely that every direction in space points toward the center. You cannot choose to move away from the center any more than you can choose to move backward in time. Falling inward becomes as unavoidable as the passage of time. And at the very center, at the point where all that mass is supposedly compressed, sits the singularity. This is where every equation dies. Einstein's general relativity predicts the singularity must exist. It says density becomes infinite. Space becomes infinitely curved, and the laws of physics as we know them stop applying. The theory points to the singularity and then goes silent. Quantum mechanics offers no better answer. At the quantum scale, space and time are supposed to behave in ways that are fundamentally incompatible with infinite compression. The two theories give contradictory descriptions of what should happen at the center. So what actually lives there? The honest answer, confirmed by every physicist working on this problem, is that nobody knows. The singularity might be real. Mass might truly be compressed to a single point of infinite density. Or the singularity might be a signal that the theories are wrong and something else, something that a correct theory of quantum gravity would describe, exists at the center. Some physicists believe the singularity does not actually exist in nature. They think a complete quantum gravity theory would smooth it out, replacing the infinite point with something small but finite. The math breaks down before it can say what. There is also a deeper puzzle at the black hole's edge. The event horizon, the point of no return, creates a problem involving information. Quantum mechanics says information about particles can never be truly destroyed, but anything that falls into a black hole and crosses the event horizon is cut off from the rest of the universe. The physicist Stephen Hawking showed that black holes slowly lose energy over vast stretches of time, eventually evaporating. When they do, what happens to the information about everything that fell in? This is called the black hole information paradox. It remains unsolved and is considered one of the deepest questions in physics today. The center of a black hole is the universe's most extreme environment, and it is the exact place where our understanding of gravity is forced to admit its limits. What lies beyond those limits is where the next chapter begins. Every force you have ever felt was carried by a particle. When light hits your eyes, photons are carrying the electromagnetic force. When an atom stays together, gluons are carrying the strong nuclear force between quarks inside it. When a radioactive atom decays, bosons carry the weak force that triggers the breakdown. These force-carrying particles are real. They have been detected. Their properties have been measured. They fit inside the standard model with precision. Gravity needs one too. Every physicist agrees on this. A complete theory of quantum gravity requires a force-carrying particle for gravity. It has been named. Physicists call it the graviton. The graviton has never been detected. No experiment has ever caught one, and the reason why reveals just how strange gravity's weakness truly is. To detect a force-carrying particle, you need to measure the force it carries at the particle level. For electromagnetism, this is straightforward. The electromagnetic force is strong enough that single photon exchanges between particles, particle accelerators detect them constantly. Gravity is so weak that the exchange of a single graviton between two particles would produce an effect far too small for any instrument ever built, or any instrument physically possible to build, to measure. The signal would be lost in noise by a factor so large it is almost meaningless to write out. Here is a way to feel that scale. To build a detector sensitive enough to catch a single graviton, you would need a detector the size of Jupiter, made of the densest material possible, and it would still take longer than the current age of the universe to register a single detection. This is not a technology problem that better engineering will solve. The physics itself makes direct graviton detection essentially impossible with any conceivable instrument. So physicists believe the graviton must exist because every other force has a carrier, and the universe appears to follow consistent rules. The math of a quantum gravity theory requires it, but belief and detection are different things. There is more to the graviton's story. Based on the math, physicists can predict what properties the graviton should have, even without detecting it. It should have no mass. It should travel at the speed of light. It should have a specific type of spin, called spin 2, which is different from all other force carriers. These predictions come from the structure of general relativity translated into quantum language. The spin 2 property is actually a clue. Any quantum particle with spin 2 naturally produces the same equations as Einstein's general relativity when you work out the math. This means the graviton is not just a guess. It is what you get when you insist that gravity must fit into the quantum framework. The particle falls out of the math automatically, but falling out of the math and existing in reality are two different things entirely. The graviton sits at the boundary between what physics requires and what physics can prove. It is the best supported undetected particle in the history of science, and its absence, or rather our inability to find it, is not the only missing piece. There is a particle that theory demands, experiments cannot reach, and whose non-detection points directly toward a structure of the universe that no human has ever seen. What comes next is even more extreme, because some physicists decided that if the particles and forces we know cannot be unified, maybe particles themselves are the wrong starting point. In the 1980s, a group of theoretical physicists made a bet that sounds like science fiction. They said, what if particles are not the fundamental building block of the universe? What if everything, every electron, every quark, every graviton, every unit of force is made of something even smaller, not smaller particles, something completely different? They called it a string. In string theory, the most basic unit of reality is a tiny loop or strand of vibrating energy. These strings are so small that if an atom were the size of the entire observable universe, a string would be the size of a single tree. They are not things you can see or touch. They exist at a scale far beyond any instrument ever built. But here is the idea. Each string vibrates, and the way it vibrates determines what kind of particle it is. A string vibrating in one pattern becomes an electron. Vibrating in a different pattern, it becomes a quark. Vibrating in a specific pattern that matches the math for a spin 2 particle with no mass, it becomes a graviton. That last point is why physicists got excited. For the first time, gravity fell out of the theory naturally. String theory did not have to add gravity as a separate ingredient. The math produced it automatically. Every version of string theory contains a graviton-like particle. This was the first theoretical framework to incorporate both quantum mechanics and gravity without the equations immediately breaking. For a decade, string theory dominated theoretical physics. Some of the most brilliant people in the field devoted their careers to it. New mathematical tools were invented to explore it. The equations were beautiful. And then came the uncomfortable part. For string theory to work mathematically, the universe cannot have just 4 dimensions. It requires 10 dimensions at minimum. Some versions require 11. We experience 4, 3 of space and 1 of time. The other 6 or 7 dimensions would have to be curled up so tightly, wrapped into shapes far smaller than an atom, that no experiment could ever detect them. This is not a prediction. It is a requirement. The theory needs extra dimensions, the way a bridge needs supports. Remove them, and the math collapses. Here is where things got complicated. A unified quantum gravity theory should ideally produce a unique description of the universe. One set of equations, one answer. String theory produced 5 different mathematically consistent versions. Then a physicist named Ed Witten showed in 1995 that all 5 versions might be different faces of a single deeper theory called M-theory, requiring 11 dimensions. What M-theory actually is remains incomplete. And none of these versions have made a prediction that any experiment has confirmed. String theory has been tested indirectly. It makes mathematical predictions about things like black hole entropy that match other calculations. But a theory of physics needs to predict something measurable in the real world, something that could potentially prove it wrong. So far, string theory has not delivered that. It remains the most mathematically developed attempt at a quantum gravity theory. It also remains entirely unconfirmed. The bet is still on the table, and the stakes just got higher. You experience 3 dimensions of space: left and right, forward and back, up and down. Add time, and you have 4 dimensions total. Every experience you have ever had fits inside those 4. But what if there are more? In 1919, a mathematician named Theodore Kaluza sent Einstein a paper proposing that the universe might have a 5th dimension. His goal was to unify gravity and electromagnetism. He showed that if you add 1 extra dimension to Einstein's equations of general relativity, the math automatically produces Maxwell's equations of electromagnetism. 2 completely separate theories fell out of one framework. Einstein sat on the paper for 2 years before publishing it. He was unsettled by how well it worked. The obvious question Kaluza could not answer was, if a 5th dimension exists, why can't we see it or move through it? A physicist named Oscar Klein offered an answer in 1926. The extra dimension is curled up on itself, looped into a circle so small that nothing we can observe interacts with it. It is everywhere, at every point in space, but so compressed that it is physically undetectable. Imagine a garden hose viewed from far away. It looks like a one-dimensional line, but zoom in and it is a cylinder with a circular dimension wrapped around it. The extra dimension was always there, it just required a closer look. This idea sat quietly for decades. Then string theory arrived and needed it desperately. For string theory to work, as covered in the previous chapter, extra dimensions are required. String theorists took the Kaluza-Klein idea and expanded it. The extra 6 or 7 dimensions would be curled into tiny geometric shapes at every point in space, shapes called Calabi-Yau manifolds, named after the mathematicians who described them. The shapes are not random. The specific geometry of those curled dimensions would determine the physical laws we experience. Different shapes would produce different particle masses, different force strengths, different constants of nature. The particular shape that produces a universe like ours, with the exact particles and forces we observe, is unknown. In the 1990s, physicists Nima Arkani-Hamed, Savas Dimopoulos and Gia Diwali proposed a different idea about extra dimensions, one that could explain the hierarchy problem from Chapter 4. They suggested the extra dimensions might be large enough that gravity could spread through them, while the other forces stay confined to a 3-dimensional surface, a membrane in higher dimensional space. If gravity leaks into extra dimensions, while the other forces do not, gravity would appear weaker in our world because its strength is diluted across more space. This could explain why gravity is so much weaker than everything else. Particle accelerators like the Large Hadron Collider at CERN were partly built to look for signatures of extra dimensions. High-energy collisions might produce particles that carry momentum in extra dimensions, showing up as missing energy in the detector. No such signatures have been found so far. The extra dimensions remain theoretical. They are required by the most developed quantum gravity framework, predicted by the most promising solution to the hierarchy problem, and completely undetected. They may be the most important things in the universe that no one has ever seen. And what happens inside those curled-up shapes, if they exist, would determine everything about why reality looks the way it does. Your head is aging faster than your feet. This is confirmed, measured, proven. Not by a huge amount, but by a real and calculable difference, because time runs slightly faster at higher altitude, farther from Earth's mass, and slightly slower closer to it. This is one of the most counterintuitive confirmed facts in all of physics, and it comes directly from Einstein's general theory of relativity. Here is the core idea. Mass bends space and time. The more mass nearby, the more time bends. And bent time runs slower. This is called gravitational time dilation. Think of time as a river. In flat, open country, the river flows quickly. As you get closer to a massive object, the riverbed warps downhill. The water slows. Objects near heavy masses, where space-time curves sharply, experience time flowing more slowly than objects far from those masses. This is confirmed in multiple ways. The clocks on GPS satellites, orbiting about 12,000 miles above Earth's surface, tick at a slightly different rate than clocks on the ground. Two effects are at work simultaneously. The satellites move fast, which slows their clocks slightly due to special relativity, but they are also farther from Earth's mass, which makes their clocks run faster due to gravitational time dilation. The net effect is that satellite clocks gain about 38 microseconds per day relative to ground clocks. That sounds tiny, but GPS systems calculate your position by measuring the travel time of signals between satellites and your phone. Microseconds translate to hundreds of feet of error. Without correcting for both effects, every single day GPS would become useless within hours. Every navigation system on Earth depends on Einstein's equations being exactly right. Astronauts on the International Space Station experience time passing slightly more slowly than people on the ground, because the station orbits at a speed and altitude where the time-slowing effect of speed outweighs the time-speeding effect of reduced gravity. When they return, they have aged a tiny fraction of a second less than they would have on Earth. Now take this to an extreme. Near the event horizon of a black hole, the mass is so concentrated, the curvature of space-time so severe, that time slows dramatically. An observer watching someone fall toward a black hole from far away would see that person slow down as they approach the event horizon, appearing to freeze at the edge. From the falling person's perspective, they cross the horizon in moments. Two clocks, two completely different experiences of time caused by the same mass. This is not philosophy. This is geometry. The shape of space-time determines the flow of time. Mass shapes space-time. The practical version of this fact runs in your pocket every day. Every time your phone gives you accurate directions, it is applying Einstein's equations in real time. Gravitational time dilation is not abstract, it is infrastructure. But the confirmation that works for GPS tells us nothing about what happens at the extremes, inside black holes, at the Big Bang, at the centers of neutron stars. There, the curves of space-time become so sharp that even time dilation equations break down. Which brings the story back to its central problem. Where physics breaks, where time dilation becomes infinite, something unknown is happening. And what happens when a human-sized object falls into that extreme region is something physics can describe perfectly, right up until the moment it cannot describe it at all. You are falling toward a black hole. Not toward the event horizon, past it, toward the center. The gravitational pull on your feet is stronger than the pull on your head. Even at a normal height of around 6 feet, the two ends of your body are at different distances from the black hole's center. The difference in gravitational force across that distance stretches you vertically while simultaneously squeezing you from the sides, like a piece of dough being pulled into a rope. Physicists call this tidal force. They also call the process it causes spaghettification. That is its actual name in the scientific literature. The tidal force exists because gravity is not uniform. It gets stronger the closer you are to the source. The side of any object closest to the mass gets pulled harder than the far side. That difference in pull across the object's length is what stretches it. You already experience a version of this every day. The moon's gravity pulls on the near side of the Earth more strongly than on the far side. That slight difference stretches the oceans. The result is tides. Twice a day, ocean water bulges slightly toward the moon. The solid land underneath also rises and falls by up to 12 inches, though it is too slow and subtle to feel. The difference in pull across the Earth's diameter from the moon is tiny. Scale that up. Put a person near a stellar black hole, one with a mass roughly 10 times the Sun, and the tidal difference across a human body becomes enormous. The feet are pulled so much harder than the head that the body stretches apart before ever crossing the event horizon. For a supermassive black hole, the kind millions or billions of times the mass of the Sun, the situation is different. The event horizon is so far from the center that tidal forces at the horizon are actually gentler. A person crossing the event horizon of a sufficiently large black hole might not feel spaghettification at that boundary at all. They could cross into the point of no return without any dramatic sensation. The destruction would come later, deeper inside, as the singularity approached. This is one of the stranger implications of the math. Size changes everything. A smaller black hole tears you apart before you cross in. A large enough one lets you through cleanly before finishing the job somewhere inside. Spaghettification is confirmed in principle. The mathematics is solid and follows directly from general relativity. Astronomers have detected signatures of stars being spaghettified by black holes, events called tidal disruption events. When a star wanders too close to a supermassive black hole, tidal forces rip it apart. The resulting burst of energy and light is detectable from Earth across billions of light years. In 2018, astronomers detected such an event and watched in real time as a star was stretched and torn, its material spiraling into the black hole. The light signature matched the theoretical predictions, so spaghettification is real. It happens to stars. It would happen to anything with physical structure that got close enough to the right kind of black hole. What physics cannot tell you is what happens after spaghettified matter reaches the center, the singularity. The matter arrives there, the equations stop. Beyond that point, gravity has won completely, and what it wins over is something that brings us to one of the most unsettling discoveries in the history of astronomy. In 1998, two teams of astronomers were racing to answer what seemed like a simple question: how fast is the universe slowing down? Everyone assumed it was slowing down. The Big Bang had sent everything flying apart roughly 14 billion years ago. Gravity, acting between all the matter in the universe, should be pulling it all back together, bit by bit. The expansion should be decelerating. The question was only how fast. Both teams were measuring distant supernovae, a specific type of stellar explosion called a Type 1a supernova. These explosions always release the same amount of energy. This makes them reliable markers. By measuring how bright they appear from Earth, astronomers can calculate exactly how far away they are. By measuring how much their light has been stretched by the universe's expansion, they can calculate how fast the universe was expanding when the light was emitted. The teams expected to find that distant supernovae showed faster expansion in the past, slowing gradually to today's rate. They found the opposite. The distant supernovae were dimmer than they should be. They were farther away than expected. The universe was not slowing down, it was speeding up. The expansion of the universe was accelerating. This result was so unexpected that both teams assumed they had made an error. They checked and rechecked for months. They looked for contamination in the data. They tested every possible systematic mistake. The result held. The universe is expanding faster now than it was billions of years ago. Something is pushing it apart. Something with enough force to overcome the combined gravitational pull of every galaxy, every cluster, every filament of matter in the observable universe. Nobody predicted this. No theory required it. No model had room for it. The teams won the Nobel Prize in Physics in 2011 for the discovery. The force driving the acceleration was given a name: dark energy. The name describes the unknown. It is not a description of what the force is. It is a label for something that clearly exists and is completely unexplained. Here is what makes the discovery more unsettling the more you examine it. Dark energy does not just slightly outpace gravity at cosmic scales. It accounts for roughly 68% of the total energy content of the entire universe. All the matter you have ever seen, every star, every planet, every galaxy, every atom in existence, makes up about 5%. Dark energy is the dominant ingredient of the cosmos by a massive margin, and nobody knows what it is. The discovery forced a rewrite of the standard model of cosmology. Every textbook that described the future of the universe had to be revised. Instead of a universe that slows, stops, and perhaps collapses under gravity, the picture became something far stranger. A universe racing apart forever, galaxies separating at increasing speed until, in the far future, the nearest ones cross a threshold and disappear from view entirely. Gravity built the universe's structure. Dark energy is dismantling it. And the source of that dismantling might be stranger than anyone imagined. Empty space is not empty. This is one of the most important confirmed facts in modern physics, and also one of the most disorienting. Quantum mechanics requires that even a perfect vacuum, a region with no particles, no matter, no radiation, is still filled with energy. This is called vacuum energy, or zero-point energy. It comes from the rules of quantum uncertainty. At the quantum scale, nothing can be perfectly still. Particles flicker in and out of existence constantly, appearing in pairs and annihilating each other in fractions of a second. The average energy in the vacuum is never exactly zero. This energy was predicted by quantum theory decades before dark energy was discovered. It was considered an odd side effect of quantum mechanics, not something with large-scale consequences. Then the 1998 supernova measurements showed that the expansion of the universe is accelerating. Physicists needed something to explain it. Vacuum energy was already there in the equations. Einstein had actually introduced a version of this idea in 1917, called the cosmological constant, a term he added to his equations to make a static universe. He later called it his biggest mistake. After 1998, it looked like it might have been his best prediction. The cosmological constant is the simplest mathematical explanation for dark energy. It says that empty space itself has an intrinsic energy. That energy has a repulsive effect on space-time, pushing regions of space apart. As the universe expands and creates more space, more vacuum energy appears. The repulsion grows, the expansion accelerates. But there is a catastrophic problem with this explanation. Quantum field theory predicts what the vacuum energy should be. The number it predicts is so much larger than what astronomers observe that the discrepancy is the most extreme mismatch between theory and measurement in the history of physics. The theoretical prediction exceeds the observed value by roughly 1 followed by 120 zeros. This is not a rounding error. It is a failure on a scale that has no parallel in science. If vacuum energy is dark energy, something unknown is suppressing it to a fraction of what theory says it should be. The alternative is that dark energy is something different entirely. Some physicists propose a dynamic energy field that fills space and changes over time, called quintessence. Unlike the cosmological constant, quintessence would not be the same everywhere and would evolve as the universe ages. It would leave subtle imprints in the distribution of galaxies and the detailed structure of the cosmic background radiation. So far, observations have not confirmed quintessence. They have also not ruled it out. A third possibility, one that physicists find deeply uncomfortable, is that dark energy reveals a fundamental error in Einstein's general theory of relativity at cosmic scales. Maybe gravity behaves differently across the full scale of the universe than the equations predict. Modified gravity theories exist. None have achieved the explanatory power of general relativity. Dark energy remains unexplained. It makes up the majority of the universe's energy content. It is actively reshaping the large-scale structure of the cosmos right now. And the leading explanation for what it is produces a theoretical prediction that is off by 120 orders of magnitude. That gap is the biggest open wound in physics today. Take the most perfect vacuum imaginable. Remove every atom, every molecule, every photon of light. Drop the temperature to absolute zero. Remove every particle you can think of. According to quantum mechanics, that space is still not empty. This is a direct consequence of a principle discovered by Werner Heisenberg in 1927, called the uncertainty principle. It states that the position and momentum of any particle cannot both be precisely known at the same time. The more precisely you know one, the less you can know the other. This principle does not come from measurement limitations. It is not about our instruments being imperfect. It is built into the fabric of reality at the quantum level. Nothing can be perfectly pinned down simultaneously. Apply this to energy. If energy were exactly zero in a region of space, it would be perfectly pinned down. The uncertainty principle forbids that. So even in a vacuum, energy must fluctuate. It cannot be zero. Particles must appear and disappear continuously to maintain that fluctuation. These flickering particles are called virtual particles. They are not fully real in the sense of persisting over time. They pop into existence in pairs, a particle and its antiparticle, and annihilate each other almost instantly. The time they exist is so short it falls inside the limit allowed by the uncertainty principle. But they are real enough to measure. The Casimir effect, first observed in 1997, demonstrates vacuum energy directly. Place two metal plates very close together, within a millionth of an inch of each other, in a vacuum. The space between them is so small that certain wavelengths of virtual particle activity are restricted. The space outside the plates has more vacuum energy than the space between them. That imbalance pushes the plates toward each other. The force is small but measurable. It matches the theoretical prediction. So vacuum energy is confirmed. Empty space pushes back because it is never truly empty. Now here is where this connects back to dark energy and gravity. If vacuum energy fills all of space and carries energy, it should contribute to the total energy density of the universe. And energy density, under Einstein's equations, affects the curvature of space-time. In other words, vacuum energy should gravitate. It should contribute to the expansion or contraction of the universe. The amount it should contribute, based on the theoretical calculation, is catastrophically larger than what observations of dark energy suggest. This has already been described, but the connection between the Casimir effect and cosmology makes it starker. The vacuum energy is real, measured, and confirmed in the lab. Its cosmological effect should be enormous. The effect observed is tiny. Something is cancelling almost all of the vacuum energy's gravitational contribution. Something is suppressing it with incredible precision. No one knows what that something is. This cancellation, so exact and so unexplained, points toward a deep flaw in the current picture of how quantum mechanics and gravity interact. The floor of empty space is vibrating. Gravity should feel it everywhere at full force. It doesn't, and understanding why might be the single most important unsolved problem in all of physics. The clue might lie in whether gravity is even what we think it is. On September 14, 2015, at 5:51 in the morning Eastern Time, two detectors in the United States picked up a signal that had traveled 1.3 billion light-years to reach them. The signal lasted less than half a second. It was a chirp, a rapid rise in frequency, then silence. And it was the sound of two black holes colliding. The detectors are called LIGO, the Laser Interferometer Gravitational Wave Observatory. One is located in Hanford, Washington. The other is in Livingston, Louisiana. They are separated by about 1,800 miles. The signal arrived at the Louisiana detector 7 milliseconds before the Hanford one, consistent with a wave traveling at the speed of light from a specific direction in the sky. Gravitational waves are ripples in space-time itself. When two massive objects spiral toward each other and merge, they release energy in the form of waves that compress and stretch the fabric of space as they pass through it. Einstein predicted this in 1916 as a consequence of general relativity. For nearly 100 years, no one could detect them. The reason is that gravitational waves are extraordinarily faint. By the time the waves from that black hole collision reached Earth, the stretching of space they caused was smaller than 1,000th the diameter of a single proton. Detecting something that small over a distance of several miles required engineering at a level that pushed the boundary of what is physically possible. LIGO works by splitting a laser beam and sending it down two tunnels, each 2.5 miles long, set at right angles. The beams bounce off mirrors and return to a central detector. When a gravitational wave passes, it stretches space in one direction and compresses it in another, changing the length of the two tunnels by different amounts. The laser beams travel slightly different distances. When they recombine, the interference pattern shifts. The shift detected on September 14, 2015, was so small it corresponds to a change in the length of a 2.5-mile tunnel by a fraction equal to dividing a proton by 1,000. Detecting that required isolating the instruments from every conceivable source of vibration: trucks on nearby roads, ocean waves miles away, seismic noise from the Earth itself. The mirrors are suspended on chains of pendulums to filter out ground motion. The lasers are among the most stable ever built. The detection was confirmed. The signal matched the theoretical prediction for two merging black holes with remarkable precision. The masses of the two black holes, the distance to the merger, the energy released, all consistent with Einstein's equations. General relativity was confirmed again 100 years after Einstein wrote it down in the most dramatic way possible. But gravitational wave detection did more than confirm a theory. It opened an entirely new way to observe the universe. Before 2015, all astronomy was electromagnetic. Everything humans knew about space came from light, radio waves, X-rays, gamma rays. All of it was electromagnetic radiation. Gravitational waves are not electromagnetic. They pass through matter without interacting with it. A gravitational wave moves through a planet as if the planet is not there. This means gravitational wave astronomy can observe events that are completely invisible to traditional telescopes: the insides of collapsing stars, the moments before and during black hole formation, potentially the gravitational echoes of the Big Bang itself. The chirp in 2015 was the first note of a new instrument. And the universe has much more to say. 1.3 billion years ago, two black holes finished a dance that had lasted millions of years. They had been spiraling toward each other, locked in a mutual orbit, each one pulling the other closer with every loop. As they closed the distance, they moved faster. The faster they moved, the more energy they radiated as gravitational waves. The more energy they lost, the tighter the spiral became. It was a feedback loop with one ending. In the final fraction of a second, the two black holes were moving at nearly half the speed of light. They merged into a single black hole. The collision released more energy in that instant than all the stars in the observable universe combined release in the same moment. Every star, every galaxy, all at once. Almost none of that energy came out as light. It came out as gravitational waves, ripples in space-time, spreading outward at the speed of light, in every direction. When those waves reached Earth 1.3 billion years later, and passed through the LIGO detectors, scientists converted the frequency of the ripples into sound. The result is a chirp, a quick rise in pitch, like a brief whistle, then nothing. It lasts about 0.2 of a second. That chirp is the most energetic event in the universe rendered into a sound a human ear can hear, and it is, by any measure, underwhelming. It sounds like a quiet pop, a small click, the gap between what that sound represents and how it sounds is one of the most striking things in modern science. The numbers behind it are almost impossible to visualize. Two black holes, one roughly 29 times the mass of the Sun and one roughly 36 times the mass of the Sun, merged into a black hole of about 62 solar masses. The missing 3 solar masses, the mass of 3 entire suns, converted entirely into gravitational wave energy in under a second. 3 suns gone. In a click, the information encoded in that chirp confirmed general relativity in a regime nobody had ever tested before. Black holes moving at relativistic speeds, merging, radiating. Every measurement matched Einstein's predictions. The masses, the spin of the resulting black hole, the ring-down pattern as the new black hole settled into a stable shape, all of it precise. Since that first detection in 2015, LIGO and its partner detector Virgo in Italy have recorded dozens of mergers, black holes colliding, neutron stars colliding with a black hole, each one a different chirp, each one a different set of masses, distances, and energies, each one confirming general relativity while simultaneously revealing how little we understand about where these black holes came from and how common such mergers are. In 2017, 2 neutron stars merged within a galaxy about 130 million light-years away. LIGO detected the gravitational waves. Telescopes around the world simultaneously detected the light from the explosion. It was the first time an astronomical event was observed in both gravitational waves and electromagnetic radiation at the same time. The merger produced a brief but extraordinarily bright flash of gamma rays, followed by a kilonova, an explosion rich in heavy elements, gold, platinum. Most of the heaviest elements in the universe are forged in moments like this. Every piece of gold that has ever existed came from a collision, like the one that produced that chirp. Gravitational wave astronomy is young. The detectors are improving. A space-based detector called LISA is planned to launch in the coming decades, capable of detecting waves from supermassive black hole mergers across billions of light-years. The universe has been speaking in gravitational waves since the beginning of time. We only just learned to listen. Stand on solid rocks somewhere on Earth, maybe the coast of Maine, maybe the cliffs of Ireland. Beneath your feet is bedrock, hundreds of feet of dense, ancient stone. It feels as immovable as anything in the world. It is rising and falling twice a day, by up to 12 inches. The moon is doing it, and almost nobody knows it happens. Most people know about ocean tides. The moon's gravity pulls on the oceans, creating a bulge of water on the side of the Earth nearest the moon. A corresponding bulge forms on the opposite side due to inertia. As the Earth rotates, different parts of the ocean pass through these bulges, producing high and low tides roughly every 12 hours. What most people do not know is that the same tidal force acts on the solid rock of the Earth's surface. Rock is not rigid in the way it seems at human scales. Under the constant, gentle differential pull of the moon's gravity, the crust of the Earth flexes. It deforms. The ground beneath you rises and falls daily, chasing the moon's position as the Earth rotates underneath it. The effect is called the solid Earth tide or the body tide. It is real, measured, and confirmed by sensitive GPS systems and instruments called tiltmeters. The rise and fall of the land surface is smaller than the ocean tide, but not by as much as you might expect. In many inland locations, the solid Earth tide is actually larger in amplitude than the ocean tide. The solid Earth tide creates real complications for precision science. The Large Hadron Collider at CERN, the particle accelerator in Switzerland, is a circular tunnel about 17 miles around. As the Earth's crust flexes under the tidal force, the tunnel's shape changes measurably. The circumference of the tunnel grows and shrinks. Scientists there have to correct for this deformation in their measurements. Radio telescopes doing precise astronomical measurements also correct for the solid Earth tide. GPS positioning at the centimeter level requires correcting for it. The tide of solid rock is not a curiosity, it is an engineering problem. Now connect this back to gravity's nature. The solid Earth tide is caused by a differential gravitational force, a tidal force, across the diameter of the Earth. The Moon's gravity is slightly stronger on the near side than on the far side. That small difference, spread across a planet, is enough to physically deform solid rock by nearly a foot, twice a day, every day. Scale that force up, take that differential and apply it at the scale of a person near a stellar black hole. The tidal force across a human body becomes so extreme that spaghettification follows. Scale it up further to the universe, and tidal forces between galaxy clusters stretch and tear the web of large-scale structure. The same physics that moves the rock under your feet also governs the most violent events in the universe. Gravity's tidal effects work from kitchen magnet scales to cosmic ones. But there is one place where tidal forces have a stranger effect than anywhere else, a place where the concept of solid ground no longer has any meaning at all, and where the density of matter becomes something your instincts cannot handle. 6 people are living in orbit right now, about 250 miles above the surface. Moving at roughly 5 miles per second, they circle the Earth every 90 minutes. They see 16 sunrises per day. They are also aging more slowly than everyone on the ground. The difference is tiny. After 6 months in space, an astronaut returns having aged roughly 3 milliseconds less than they would have on Earth. It is not noticeable in daily life, but it is real, confirmed, and explained precisely by the equations of both special relativity and general relativity working simultaneously. 2 effects are at work, and they pull in opposite directions. The first is velocity. The space station moves at about 17,500 miles per hour. According to special relativity, the faster an object moves, the slower time passes for it relative to a stationary observer. At the station's speed, this effect causes the onboard clocks to tick slightly slower than ground clocks. This slows aging relative to people on Earth. The second is gravity. The station orbits at an altitude where Earth's gravitational pull is weaker than at the surface. According to general relativity, weaker gravity means less curvature of space-time, which means time runs faster. This effect causes the onboard clocks to tick slightly faster than ground clocks. This would make astronauts age faster relative to people on Earth. The 2 effects partially cancel, but not completely. The velocity effect is larger. The net result is that astronauts age slightly more slowly than they would on the ground. After a long mission, they return having accumulated slightly less biological time than their twin on Earth. This is not theoretical. Scott Kelly spent nearly a year on the station, while his identical twin brother Mark stayed on Earth. Researchers measured changes in gene expression, telomere length, and microbiome composition between the 2 brothers. The biological differences were real and measurable. After Scott returned, most reversed. Some did not. The time dilation itself was confirmed indirectly through the biology and directly through atomic clock comparisons on previous missions. Now push the scenario to its logical extreme. Move the station closer to Earth, into a lower orbit where gravity is stronger. The gravitational time dilation effect increases. Move it lower still. Eventually, the increase in gravitational time dilation outweighs the velocity effect, and the astronaut ages faster in space than on Earth's surface. Move the scenario to a neutron star. The surface gravity of a neutron star is roughly 200 billion times stronger than Earth's. Time dilation at the surface would be extreme. A clock sitting on the surface of a neutron star would tick measurably slower than a clock far away in empty space. If you could sit on the surface for what felt to you like an hour, a much longer time would have passed for everyone else in the universe. Move the scenario to the event horizon of a black hole. Time dilation approaches infinity. From an outside observer's perspective, a clock falling toward the event horizon appears to slow, then freeze, never quite reaching the boundary. Time dilation becomes so extreme that the clock appears to stop. These are all confirmed consequences of the same equations. The same physics that causes a 3-millisecond difference for a 6-month mission produces the complete freezing of time at a black hole's edge. Gravity does not just pull objects together. It shapes the rate at which time moves for everything embedded in it. And the consequences of that, taken to their extreme, produce one of the densest objects in the known universe. Imagine a star roughly 10 to 20 times the mass of the Sun. It burns for millions of years, fusing hydrogen into helium, helium into carbon, carbon into heavier elements, working its way up through the periodic table. When it finally exhausts its nuclear fuel, the core collapses. The collapse takes less than a second. The outer layers of the star rebound off the collapsing core and blow outward in a supernova explosion, one of the most energetic events in the universe. The energy released in that explosion exceeds what the Sun will produce over its entire 10 billion-year lifetime. What remains at the center is a neutron star. A neutron star typically contains roughly 1 to 2 times the mass of the Sun, but it is compressed into a sphere about 12 miles across. 12 miles a city. The entire mass of a star, crammed into something you could walk across in a few hours if the surface gravity were not 200 billion times what you experience on Earth. The density of a neutron star is difficult to picture. The electrons and protons inside ordinary atoms have been forced together by the collapse, combining into neutrons. The empty space inside atoms, which makes up essentially all of the volume of normal matter, has been eliminated. What remains is pure nuclear density, neutrons packed together as tightly as the nucleus of an atom. A teaspoon of neutron star material would weigh about 10 billion pounds on Earth. 10 billion pounds. A single teaspoon. That is roughly the mass of every car ever built in human history, compressed into a volume smaller than a sugar cube. Neutron stars spin. When they first form, conservation of angular momentum accelerates their rotation dramatically, the same way a spinning skater speeds up by pulling in their arms. A neutron star can rotate hundreds of times per second. Some rotate over 700 times per second, a rate so extreme that the equator of the star moves at a significant fraction of the speed of light. When a neutron star's magnetic field is aligned to beam radiation toward Earth, we detect regular pulses of radio waves, or X-rays, with each rotation. These are called pulsars. The regularity of their pulses is so precise that the first one detected in 1967 was briefly labeled LGM-1, standing for Little Green Men, because researchers considered whether it might be an artificial signal. It was not. It was physics producing a clock more accurate than almost any built by humans. Neutron stars also confirmed gravitational waves indirectly before LIGO detected them directly. In 1974, 2 physicists found a pulsar orbiting another neutron star. Over years of observation, the orbital period decreased at exactly the rate general relativity predicted, because the system was losing energy by radiating gravitational waves. They won the Nobel Prize in 1993 for this indirect confirmation. At the center of a neutron star, conditions become extreme enough that the known equations of nuclear physics start to fail. What state matter exists in at the core, whether it remains neutrons, dissolves into quarks, or becomes something else entirely, is unknown. Neutron stars are the densest observable objects in the universe, and their interiors are genuinely unexplored territory. They sit right at the boundary of what physics can describe. One step further in density, and you cross into a black hole. One step further in our understanding, and you reach the same blank that sits at the center of everything else in this story. In 1937, an astronomer named Fritz Zwicky predicted something extraordinary. He said that clusters of galaxies could act as natural telescopes, bending the light of more distant objects behind them and magnifying them for observers on Earth. Nobody took him seriously for decades. The idea was mathematically correct, following directly from Einstein's general relativity, but it seemed too exotic to matter practically. By the 1980s, astronomers started finding it everywhere. Photographs of galaxy clusters began revealing strange arcs and rings of light around them. These were not separate objects. They were single background galaxies, their light bent into curves and stretched into arcs by the gravity of the cluster sitting between them and Earth. In some cases, the same background galaxy appeared multiple times in the same image, its light taking different curved paths around the cluster to reach the telescope. The effect is called gravitational lensing. The cluster acts like a massive, imperfect lens, and it works for a reason that should not make sense if you think about gravity the old way. Light has no mass. Under Newton's gravity, only mass attracts mass. A beam of light having no mass should feel no gravitational pull and travel in a perfectly straight line past any massive object. Einstein's prediction was exactly twice Newton's. Under general relativity, gravity is not a pull between masses. It is the curvature of space-time. Light travels through space-time. It follows the curves. Mass bends space-time, and light, traveling through that bent space, takes a curved path. The 1919 eclipse measurement confirmed this for the Sun. The bending matched Einstein's number, not Newton's. Light follows space-time geometry, regardless of whether it has mass. Gravitational lensing turned this confirmed prediction into a tool. Astronomers use lensing to see objects too faint and too distant to observe directly. The Hubble Space Telescope has imaged galaxies billions of light years away, their light amplified and distorted by intervening clusters. Without lensing, those galaxies would be invisible. Lensing also became a way to map invisible matter. When astronomers measure how strongly a cluster bends background light, they can calculate how much mass is doing the bending. In the 1980s and 1990s, those calculations kept returning mass estimates far higher than the mass of all visible stars and gas in the cluster. Something massive and invisible was contributing to the lensing. This became some of the strongest evidence for dark matter, a completely separate mystery from dark energy. Dark matter appears to be matter that does not interact with light at all. It neither emits nor absorbs radiation. It is only detectable through its gravitational effects. It makes up roughly 27% of the universe's total energy content, while all visible matter is only about 5%. So gravitational lensing confirmed Einstein, enabled deep space observation, and revealed that most of the matter in the universe is invisible. 3 enormous results, all from the bending of light by curved space-time. And yet the underlying mechanism, the quantum nature of how gravity curves space, the particle that carries that curvature, the connection between the geometry of space-time and the quantum fields that fill it, remains as unknown as it was in 1915. Every confirmation of general relativity makes the failure to unify it with quantum mechanics feel more urgent. Return to the refrigerator magnet. Return to the paperclip. The entire gravitational pull of the Earth, defeated instantly by a household object worth $2. The previous chapters have touched on this gap. Now it is time to sit with it and understand why it is not just strange, but genuinely threatening to the coherence of physics as a whole. The hierarchy problem is this: there is no natural reason within current physics for gravity to be as weak as it is. The other 3 forces have strengths that can be understood in terms of each other, connected through the mathematics of the Standard Model. Gravity sits outside that framework entirely at a strength so far below the others that even expressing the ratio requires writing it as 1, followed by roughly 40 zeros. This kind of extreme number, appearing without explanation in the fundamental constants of nature, is something physicists call unnatural. Naturalness is not an aesthetic preference. It is a principle. When a theory contains a number that must be tuned to extraordinary precision to produce the universe we observe, without any deeper reason for that tuning, it suggests the theory is incomplete. Here is a way to feel why this matters. Suppose you are building a house of cards on a table, and someone tells you that one of the cards happens to be perfectly balanced on its corner, staying upright with no support. you could accept that as coincidence. But if the entire house depends on that one card being in perfect balance, and removing it collapses everything, you start to suspect something is holding it up that you cannot see. The hierarchy problem is the card. The weakness of gravity is so extreme that it raises the suspicion that something unseen is responsible, something that physics has not yet discovered. Supersymmetry, often shortened to SUSY, proposes that every particle in the standard model has a heavier partner particle. These partners would cancel the quantum corrections that would otherwise inflate the mass of fundamental particles to enormous values, keeping gravity's relative weakness stable. Supersymmetry was one of the most anticipated predictions in particle physics. The Large Hadron Collider at CERN was partly designed to find evidence of it. Years of collisions at the highest energies ever achieved in a laboratory have found no trace of supersymmetric particles. The extra-dimension explanation, mentioned in Chapter 11, proposes that gravity spreads across more dimensions than the other forces, diluting its strength in our observable universe. This is mathematically coherent but experimentally unconfirmed. A third approach questions whether the hierarchy problem is actually a problem. Some physicists argue that the universe's constants simply are what they are, selected perhaps by a vast landscape of possible universes, each with different constants. In a universe where gravity were much stronger, galaxies might not form, stars might not last long enough for life to develop, and no one would be here to ask the question. This is called the anthropic argument. Many physicists find it deeply unsatisfying because it cannot be tested. The hierarchy problem remains open, and its openness sits at the center of every attempt to build a complete theory of physics. Something is missing. The gap in gravity's strength is not a curiosity. It is a clue, and the person who first decoded Newton's math well enough to ask why it worked knew that too. Albert Einstein died on April 18, 1955, at 76 years old, in Princeton, New Jersey. On the hospital bedside table were pages of equations. He was still working, still trying, still chasing the same idea he had begun pursuing 30 years earlier. He never finished it. He never came close. After 1915 and the general theory of relativity, Einstein became the most famous scientist alive. He had rewritten the laws of gravity, predicted black holes, explained the movement of light. He had done what Newton had not, given a picture, a physical mechanism, for how gravity worked. Then he set out on a new mission. He wanted to unify gravity with electromagnetism into a single theory, one framework, one set of equations that described all of physics. At the time, only two fundamental forces were known: gravity and electromagnetism. The nuclear forces had not yet been discovered. Einstein believed that if two forces existed, they must be expressions of one deeper reality. He spent the rest of his life trying to find it. He tried extending his geometric approach. General relativity described gravity as the curvature of a four-dimensional space-time. Maybe electromagnetism could be explained by adding more dimensions to the geometry. This was the Kaluza-Klein idea. Einstein explored versions of it for years. None produced a working theory. He tried modifying the mathematical structure of his original equations. He tried asymmetric generalizations of his tensors. He tried unified field theories with additional geometric degrees of freedom. He published papers throughout the 1930s and 40s proposing approaches, working through the mathematics, then abandoning them when they failed to produce the right predictions. His colleagues grew increasingly skeptical. The physics world was moving on. Quantum mechanics was developing rapidly. The standard model was taking shape. The path to unification, most physicists believed, ran through quantum theory, through particles and fields, and the mathematical language of quantum field theory. Einstein rejected quantum mechanics as a fundamental theory. He famously said that God does not play dice, expressing his belief that the probabilistic nature of quantum mechanics reflected human ignorance rather than the true workings of reality. He believed a deeper, deterministic theory existed underneath. This put him at odds with nearly every other leading physicist, while Bohr, Heisenberg, Pauli, Dirac, and Feynman built the quantum framework that would eventually explain 3 of the 4 fundamental forces with extraordinary precision. Einstein worked alone, on a path most considered a dead end. He was aware of the isolation. He wrote to friends that he was pursuing a direction others thought foolish. He doubted himself. He kept going. His final years produced no new physics. The unified field theories he published in his last decade have been studied and found to be mathematically interesting, but physically empty. They do not describe the world, but his goal was not wrong. The unification of gravity with the other forces remains the central unsolved problem in physics today. The tools Einstein lacked, quantum field theory, the Standard Model, string theory, loop quantum gravity, are the tools modern physicists bring to the same problem he faced. He was right that the problem existed and mattered. He was wrong about how to solve it, and too committed to his geometric approach to follow the quantum path that might have gotten him further. Einstein did not fail because he was not brilliant enough. He failed because the answer has not been found by anyone, not in his lifetime, and not in the 70 years since. Everything in this script has described gravity as a force, the weakest force, the force that builds galaxies, the force that bends light, the force that slows time. But there is a serious, actively debated position in theoretical physics that gravity is not a force at all. Einstein already moved partway toward this idea. In his general relativity, gravity is not a push or a pull between objects. It is the curvature of space-time. Objects follow curves in that geometry. They do not accelerate because a force is acting on them. They move in the straightest possible path through curved space. The path curves because space curves. In this view, standing on the surface of the Earth is the deviation from natural motion. You are being pushed upward by the electromagnetic force of the ground under your feet, prevented from following your natural freefall path toward Earth's center. When you are in orbit or in freefall, you are following gravity, moving in a straight line through curved space, with no force acting on you at all. Astronauts on the space station feel weightless. The popular explanation is that they are in zero gravity. This is wrong. Earth's gravity at the station's altitude is about 88% of its surface value. The astronauts feel weightless because they are in free fall, following the geometry of space-time, with no electromagnetic force pushing back against that motion. Free fall feels like floating because floating and free fall are the same thing. If gravity is geometry and not a force, then the graviton, the force-carrying particle physics says gravity must have, is in tension with this picture. Forces have carriers, geometry does not. This is one layer of the debate. A deeper layer comes from a theoretical physicist named Eric Verlinde, who proposed in 2010 that gravity might be an emergent phenomenon. In this idea, gravity does not exist at a fundamental level. It arises from the statistical behavior of a more fundamental system, specifically from the way quantum information is organized in space. Verlinde drew on a connection between black hole thermodynamics and information theory. In the 1970s, physicists Jacob Bekenstein and Stephen Hawking showed that black holes have entropy, a measure of disorder or information content, proportional to their surface area. This suggested a deep connection between gravity, thermodynamics, and information. Verlinde argued that gravity is similar to entropy itself. Entropy is not a fundamental force, it is an emergent property of large systems, arising from the statistical behavior of many microscopic components. Water flows downhill not because downhill is a force, but because arrangements where water is lower are vastly more likely than arrangements where it is higher. Verlinde argued gravity works analogously, emerging from the tendency of space-time systems to move toward higher entropy states. If Verlinde is right, searching for a graviton is the wrong approach entirely. There is no fundamental particle of gravity to find. Gravity appears because of information. because of the way quantum systems arrange themselves statistically. This idea is controversial and not accepted by most physicists, but it has not been disproven either. It sits in the category of a serious theoretical proposal that cannot yet be tested. Whether gravity is a force, a geometry, or an emergent property of information, one thing is common to all three descriptions. Its behavior at the quantum level remains unexplained. In 2010, Erik Verlinde published a paper that split the theoretical physics community in two. Half dismissed it quickly, half could not stop thinking about it. His core claim was that gravity is not written into the laws of physics at a fundamental level. It appears. It emerges from something deeper, the way temperature emerges from the motion of individual molecules, or the way pressure emerges from countless individual air molecules bouncing against a surface. No single molecule has temperature, no single molecule has pressure, but collect enough of them, and these properties arise inevitably from the statistics of their behavior. Verlinde argued that gravity arises from entropy and information, specifically from the behavior of quantum information encoded on surfaces in space-time. The starting point for this idea comes from black hole physics. In the 1970s, Jacob Bekenstein noticed something strange. The entropy of a black hole, the measure of how much information it contains about everything that has fallen in, is proportional to its surface area, the event horizon. The bigger the surface, the more entropy. This is bizarre for a simple reason. In ordinary physics, entropy is a property of volume. A box of gas has entropy proportional to how many particles fit inside it. Black holes reversed this. Their information is stored on their surface, not their interior. This became known as the holographic principle, the idea that a region of space can be fully described by information on its boundary. Verlinde used this principle as a starting point and argued that the same logic applies everywhere in space, not just at black holes. Information is encoded on surfaces throughout space-time. When a massive object is present, it changes the entropy distribution on these surfaces. Objects move in ways that maximize entropy. The movement that maximizes entropy in the presence of mass looks exactly like gravity. Gravity in this picture is what happens when systems move toward higher entropy. It is thermodynamic. It is statistical. It is not a fundamental force, but an inevitable outcome of the way quantum information organizes itself. In 2016, Verlinde published an extended version of his theory that made a specific prediction. If gravity emerges from quantum entanglement in space-time, then in regions where dark matter effects are observed, the theory can explain them without requiring any actual dark matter particles. The emergent entropic force produces the same gravitational effects attributed to invisible dark matter. Several research teams tested this prediction against galaxy rotation curves, the data that originally made dark matter famous. Results were mixed. Some galaxy data matched Verlinde's predictions well, others did not. The theory remains contested. There is also a deeper connection to quantum entanglement that other physicists have explored. Juan Maldacena and Mark van Ramsdonk showed through mathematical work that quantum entanglement between distant particles in certain theoretical spaces is directly connected to the geometric connectivity of the space-time those particles inhabit. Remove the entanglement, and the space-time falls apart, literally becoming disconnected. This suggests that the fabric of space-time might be stitched together by quantum entanglement. Geometry would emerge from quantum correlations. Gravity would be a consequence of how entanglement organizes information across space. These ideas remain theoretical, but they point in a consistent direction. The deepest explanation for gravity may not look like a force at all. It may look like information. It is the most tested theory in the history of science. Every prediction it has made has been confirmed. Its accuracy, in some measurements, extends to more than 10 decimal places. No other framework built by human beings matches experimental reality with that level of precision. Physicists call it the standard model of particle physics, and it is, by every empirical measure, a triumph. It does not contain gravity. This is not an oversight. It is not a gap waiting to be filled in the next edition. It is a structural feature, a hard wall inside the theory, beyond which the Standard Model cannot go. The Standard Model describes 3 of the 4 fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. It describes all known fundamental particles: the quarks that make up protons and neutrons, the electrons and their heavier cousins, the neutrinos, and the force-carrying bosons. Every particle in the model has been detected. Every force in the model has been measured. The Higgs boson, predicted by the model in 1964, was confirmed at CERN in 2012 after decades of searching. Each force in the Standard Model is carried by a specific boson: the electromagnetic force by photons, the strong force by gluons, the weak force by the W and Z bosons. These particles are the mechanism by which forces act. They are exchanged between matter particles, and those exchanges produce the forces we observe. Gravity has no boson in the Standard Model. The graviton is not in the table. The model has no mechanism to include it. Every attempt to write a quantum version of gravity that fits inside the mathematical framework of the Standard Model fails because the resulting theory is not renormalizable, as covered in Chapter 7. Infinities appear and cannot be removed. What makes this remarkable is that the Standard Model's mathematical language, quantum field theory, is the most powerful tool physicists have. It can describe particles, forces, symmetries, and interactions at the deepest level currently accessible. It is the language that unified electromagnetism, the strong force, and the weak force into one consistent picture. That same language breaks when applied to gravity. The failure is mathematical, but its implications are physical. The universe contains gravity. The universe contains quantum particles. At every point in space, both are present. They both act on the same objects. A proton inside the Sun is subject to both the strong force and gravity simultaneously. The Standard Model can describe the strong force acting on that proton in extraordinary detail. It has nothing to say about the gravity acting on the same proton at the same time. This means the 2 best frameworks humans have built for understanding physical reality are describing overlapping territory using incompatible tools. Physicists know this. They have known it for decades. Progress has been genuine on the mathematical side, with string theory, loop quantum gravity, and other approaches making headway on partial problems. But a complete testable theory that unifies gravity with the Standard Model has not been achieved. The Standard Model's blind spot is not a minor limitation. It is the frontier of physics. Everything past it is unexplored. The most abundant substance in the universe has no agreed-upon name for what it actually is. Dark energy is a label for a measured effect, not an identified thing. Astronomers know it exists because the universe's expansion is accelerating. They know it makes up roughly 68% of the universe's total energy. They do not know its physical nature. They are not equally supported. None are confirmed. The first is the cosmological constant. Einstein introduced this term in 1917 as a mathematical fix to make his equations describe a static universe. He assigned the symbol lambda to it, and it represented an energy density intrinsic to space itself. When he learned the universe was expanding rather than static, he removed it. When the acceleration of expansion was discovered in 1998, the cosmological constant was reinstated. In this interpretation, dark energy is the energy of empty space. It is constant everywhere, at all times, and does not dilute as the universe expands. As the universe grows and space increases, the total amount of dark energy grows with it, driving ever faster expansion. The cosmological constant fits the data better than any competing model. The problem is the magnitude. As described in Chapter 15, quantum field theory predicts what the energy density of empty space should be, and the prediction overshoots the observed value by an absurd margin. 1 followed by 120 zeros. Something must be suppressing the quantum vacuum energy to its observed level with extraordinary precision. The mechanism for that suppression is unknown. The second proposal is quintessence, a dynamic energy field that fills space but changes over time. Unlike the cosmological constant, quintessence is not uniform. It can vary across space and evolve as the universe ages. Some versions of quintessence predict that the rate of acceleration changes over time, and that dark energy may weaken or strengthen in the future. Current observations cannot distinguish quintessence from the cosmological constant with enough precision to confirm or rule it out. The third proposal is that dark energy does not exist as a separate ingredient. Instead, general relativity is wrong at cosmological scales. Einstein's equations may need modification when applied across billions of light years. Modified gravity theories attempt to explain the acceleration without introducing new energy. These theories have trouble explaining all the observational data simultaneously. None have replaced general relativity. A newer development is worth noting. In 2024 and 2025, results from large-scale galaxy surveys suggested that the expansion rate of the universe may not be as constant as the cosmological constant predicts. The data is not conclusive, but it hints that dark energy might evolve over time, pointing away from the simplest cosmological constant and towards something dynamic. If dark energy changes over time, the cosmological constant is ruled out. That would be one of the most significant results in cosmology in decades. The implications extend beyond physics. Dark energy determines the ultimate fate of the universe. If it remains constant, the expansion accelerates forever, and the universe slowly empties as galaxies retreat beyond the observable horizon. If dark energy strengthens over time, the acceleration could tear apart not just galaxies, but eventually stars, planets, and atoms themselves, in an event called the Big Rip. If dark energy weakens or reverses, gravity could eventually win, pulling the universe back in a big crunch. The nature of dark energy is a question about how everything ends. There is a line in the universe. On one side, Einstein's gravity rules: smooth, continuous, geometric. It predicts the path of planets, the bending of light, the ticking of clocks near massive objects, all with extraordinary accuracy. On the other side, quantum mechanics rules: discrete, probabilistic, particle-based. It predicts the behavior of atoms, the emission of light, the decay of particles, all with extraordinary accuracy. The two sides do not overlap well, and the line between them, the scale at which one must give way to the other, has never been found. This is not a metaphor. There is a specific scale in physics called the Planck length, roughly 1.6 times 10 to the negative 35th meters, a decimal point followed by 34 zeros, and then a 16. This is the scale at which quantum gravity effects are expected to become significant, where the fluctuations of quantum mechanics begin to affect the geometry of space-time itself. At this scale, the smooth fabric of space-time that Einstein described may dissolve into something completely different. Quantum foam is one proposed description, a picture of space-time as a churning, fluctuating structure at the smallest scales, nothing like the smooth continuum we observe. At scales far above the Planck length, the foam averages out and space appears smooth. At the Planck scale, it might look nothing like space as we understand it. The problem is that the Planck length is so small, it is physically impossible to probe directly. The most powerful particle accelerator ever built, the Large Hadron Collider, reaches energies about 15 orders of magnitude too low to probe the Planck scale. Building an accelerator capable of reaching Planck energies would require a machine the size of the Milky Way galaxy. So the boundary exists theoretically, but is inaccessible experimentally. Physics cannot reach it from below. It can be studied indirectly. The early universe, in the first instance after the Big Bang, reached temperatures and densities where Planck scale physics was relevant. The pattern of density fluctuations imprinted on the cosmic microwave background, the faint glow of radiation left over from the early universe, carries information about those early moments. Future measurements of this background radiation may reveal signatures of quantum gravitational effects from the universe's first instance. Gravitational wave astronomy offers another indirect window. As detectors improve and space-based observatories come online, they may detect primordial gravitational waves produced in the early universe during an event called inflation, the period of rapid expansion believed to have occurred immediately after the Big Bang. The spectrum of those waves could carry imprints of quantum gravity. The boundary between classical gravity and quantum behavior sits at a scale that no instrument can reach directly. But the universe itself passed through that boundary once, at its beginning. The echoes of that passage may still be detectable. Finding those echoes would be the closest thing to seeing what lies on the other side of the line nobody has crossed. String theory is not the only attempt to unite gravity with quantum mechanics. It is the most famous one. But for decades, a quieter, stranger, and in some ways more radical approach has been developed in parallel. It is called loop quantum gravity. String theory starts with the standard model and tries to add gravity. Loop quantum gravity starts with general relativity and tries to make it quantum. They begin from opposite ends of the same problem, and they arrive at very different pictures of what space-time actually is. The central claim of loop quantum gravity is this: space is not continuous. It is not a smooth fabric that can be divided infinitely into smaller and smaller pieces. At the smallest scale, space is made of discrete, indivisible units, like pixels on a screen. These units are called spin networks, and the minimum possible length is the Planck length. This is a radical departure from every prior picture of space. Newton's space was infinite and flat, a stage on which matter moved. Einstein's space was dynamic, curved by mass. But both were continuous. Both could, in principle, be divided infinitely. Loop quantum gravity says that is wrong. Zoom in far enough, and space stops dividing. You hit the pixel. The theory builds space itself from a network of quantum nodes and links. Each node represents a tiny chunk of space. The links between nodes represent the connections between those chunks. The geometry of space, the distances, and angles and curvature emerges from the structure of this network. When mass is present, the network adjusts, and that adjustment is what general relativity describes as the curvature of space-time. Loop quantum gravity makes specific predictions. The most important is that space-time has a discrete structure at the Planck scale. A key consequence of this is that there should be a minimum possible volume and a minimum possible area. The theory also predicts modifications to the dispersion of light at very high energies, potentially detectable in light arriving from extremely distant gamma-ray bursts. Astronomers have searched for these modifications. The results so far are inconclusive. The theory also addresses the singularity problem that haunted general relativity. If space cannot be divided infinitely, then infinite density cannot exist. The singularity at the center of a black hole, where general relativity predicts infinite compression, is replaced in loop quantum gravity by an extreme but finite density. The equations survive. They do not break. The singularity is resolved by the discrete nature of space. The same resolution applies to the Big Bang. In loop quantum gravity, the universe did not begin from an infinitely dense point. The extreme compression of the early universe reached the Planck density and then bounced, a moment called the Big Bounce. Before the Big Bang, another universe may have contracted, reaching maximum compression, and then expanding outward into what we call the Big Bang. Loop quantum gravity has not been confirmed. It makes predictions that are extremely difficult to test with current technology. Its mathematics is not as developed as string theories, and it does not naturally incorporate the standard model of particle physics. But it offers something string theory has struggled with: a picture of what space actually is. at the deepest level that does not require extra dimensions or strings, just quantum geometry, just the network, and right at the point where the network replaces the singularity, where the Big Bounce replaces the beginning of time, something waits that no theory has yet fully described. You have spent your entire life experiencing the world at human scales: rooms, roads, mountains. The farthest you can see with your naked eye on a clear night is roughly 2.5 million light-years. To the Andromeda Galaxy, that is vast. Go the other direction, shrink, down past centimeters to millimeters, smaller, into the world of cells, around 10 micrometers across, smaller, into bacteria, around 1 micrometer, smaller, into viruses, around 100 nanometers, smaller, into individual atoms, around 1/10 of a nanometer. At this scale, quantum mechanics begins to dominate. The electron around a hydrogen atom is not a tiny marble orbiting a nucleus. It is a probability cloud, a blur of possible positions, defined by a wave function that gives the odds of finding it in any given location. Keep going. Into the nucleus, protons and neutrons are about 1 femtometer across. Inside them, quarks are bound by gluons, never found alone, always confined in groups. Below the quark scale, physics becomes speculative. No experiment has probed deeper than this. Shrink another 20 orders of magnitude, past anything any accelerator has explored, past the scale of any proposed physical structure, down to the Planck length. At this scale, space and time as we know them likely cease to exist in the form we experience them. The uncertainty principle, applied to space-time itself, predicts fluctuations in geometry so violent that the concept of a smooth surface breaks down entirely. Space-time may become a churning, disconnected foam where distances cannot be meaningfully defined. The direction of time may become ambiguous. This is the Planck scale, and it is the physical boundary of what any theory must describe to be complete. A true theory of quantum gravity must produce sensible, finite answers at this scale. It must explain what space and time actually are when you can no longer divide them further. Here is what is known. At this scale, gravity and quantum mechanics must both be relevant simultaneously. Gravity, which normally dominates at large scales and is irrelevant at small scales, becomes important again at the Planck scale, because the energy density required to probe it is so extreme that the gravity of that energy itself becomes significant. This is why every theory fails there. General relativity, designed for smooth geometry, hits the point where geometry breaks. Quantum mechanics, designed for particles in a background space-time, hits the point where the background no longer exists. String theory hopes to avoid the problem by replacing point particles with extended strings, so the Planck scale is never truly probed. The minimum size of a string sidesteps the singularity. Loop quantum gravity confronts the problem directly by making space discrete, so you hit the pixel and stop rather than zooming through to infinite density. Neither has been confirmed. What the universe actually looks like at the smallest possible scale is the deepest unknown in all of physics. The answer would complete the picture of reality from its largest structures down to its most fundamental building blocks. Every other mystery in this story leads here. The weakness of gravity, the failure of the Standard Model, the breakdown of equations at singularities, the nature of dark energy, all of them point towards something happening at this scale that no one has seen. And the implications of whatever is discovered there extend far beyond physics. A paperclip, a refrigerator magnet, the entire gravitational pull of the Earth, defeated by $2 worth of plastic and metal. That gap, first described in Chapter 4, has never gone away. Gravity is not just weaker than the other forces, it is so much weaker that the difference demands an explanation. One explanation is that gravity is leaking. In 1999, 3 physicists named Nima Arkani Hamed, Savas Dimopoulos and Gia Diwali published a paper proposing that the universe has extra dimensions large enough to solve the hierarchy problem. In their model, the particles and forces of the standard model are confined to a three-dimensional surface, a membrane floating in a higher dimensional space. Gravity, however, is different. Gravity propagates through all dimensions, including the extra ones. If this is correct, the gravity you experience is only a fraction of gravity's full strength. The rest has spread out into dimensions you cannot access or detect. What feels like extremely weak gravity in your three-dimensional world is actually gravity diluted across extra-spatial dimensions. In its full higher dimensional strength, gravity would be comparable to the other forces. The hierarchy problem disappears. The extra dimensions in this model do not need to be as small as the Planck length. They could be as large as a fraction of a millimeter, far larger than the dimensions required by string theory. This made the proposal testable in a way many extra dimension theories are not. The test is based on Newton's inverse square law. At normal distances, the gravitational force between two objects weakens with the square of the distance between them. If gravity leaks into extra dimensions, this relationship would change at small scales. At distances comparable to the size of the extra dimensions, gravity would weaken faster than the inverse square law predicts, spreading into the extra dimensions instead of staying confined to three-dimensional space. Experiments were designed to measure gravity at very small distances below a millimeter to look for deviations from the inverse square law. These are called short-range gravity tests. They use sensitive torsion balances, precise instruments that detect tiny gravitational forces between closely spaced objects. So far, gravity has followed the inverse square law down to scales below 50 micrometers. No deviation has been found. This rules out extra dimensions larger than about 50 micrometers. The window for large extra dimensions as a solution to the hierarchy problem has narrowed, though it has not completely closed. Particle accelerators offer a different test. If gravity leaks into extra dimensions, high-energy collisions might produce gravitons that escape into those dimensions, carrying away energy that detectors cannot measure. This would appear as missing energy in collision data. CERN's experiments have searched for this signature. No confirmed detection. The extra dimension explanation for gravity's weakness remains theoretically elegant and experimentally unconfirmed. It is one of the most creative attempts in modern physics to solve one of its most stubborn puzzles. And it leads directly to the final question, the one that sits underneath every chapter in this story, the one that has no answer yet, the one that defines what physics will be doing for the next century. Newton gave us equations that worked without explanation. Einstein gave us a picture that broke at the smallest scales. The standard model unified three forces and left gravity behind. String theory offered a mathematical framework and no confirmed prediction. Loop quantum gravity reimagined space as discrete and has not been tested. Dark energy was discovered in 1998 and remains unexplained in 2026. This is where physics stands. The central unresolved problem is the same one that has been circling through every chapter of this story. Gravity does not fit. Every other force has been brought into a unified mathematical framework. Gravity refuses. Every other force has a confirmed quantum description. Gravity does not. Every other force has a detected carrier particle. Gravity's carrier has never been found. This is not a failure of physicists. The people working on this problem are among the most brilliant humans alive. The mathematics they have developed to approach it has advanced entire fields of pure mathematics as a side effect. String theory, while unconfirmed as a physical theory, generated mathematical tools used by mathematicians in completely unrelated areas. Loop quantum gravity introduced new structures in geometry. The problem is hard in a way that few other problems in history have been hard. What solving quantum gravity would actually change is worth sitting with. A complete theory of quantum gravity would explain the moment of the Big Bang, not gesture toward it while admitting the equations break. It would explain what happens at the center of a black hole. It would resolve whether the singularity is real or a sign that general relativity is wrong. At that scale, it would potentially explain the weakness of gravity, either through extra dimensions or through some deeper structure of space-time that makes the hierarchy natural rather than arbitrary. It would almost certainly say something about dark energy. The cosmological constant problem, the mismatch between the predicted and observed vacuum energy, is fundamentally a problem about the intersection of quantum mechanics and gravity. Solve one, and you likely illuminate the other. A quantum gravity theory would also answer the question of what space and time actually are. Einstein showed that they are dynamic, that they can bend and stretch, but in his theory they remain a continuous background. Quantum mechanics suggests that at the deepest level, nothing is continuous. Something discrete may underlie space and time. A quantum gravity theory would tell us what. The implications extend beyond physics. Our understanding of time's direction, of causality, of what it means for something to happen, all rest on the current picture of space-time. A revised picture could alter those foundations. None of this is guaranteed. Science does not promise answers on any timeline. The unification of electricity and magnetism took 2 centuries after their separate discoveries. The unification of electromagnetism and the weak force took decades of failed attempts before Glashow, Salam and Weinberg found the right approach. Gravity has been resisting unification for 100 years since quantum mechanics was born. The next breakthrough could come from a new prediction confirmed at a particle accelerator, from a gravitational wave signature that matches a quantum gravity model, from a precise measurement of light from a distant gamma-ray burst, revealing the granularity of space, from a theoretical insight that recasts the problem in a way that makes the current failures obvious in hindsight, or it could come from an entirely new direction nobody has thought of yet. That is where physics ends and the unknown begins. Right here, right now, in 2026, with every confirmation of general relativity, with every particle accelerator collision, with every chirp detected by LIGO, the boundary gets better mapped. The answer is out there. Someone alive today may find it.